Social bonds truly help in the growth of an individual, and personally, I have seen myself grow in these 3 years like never before.
Hi, name's Nabil and I'm from BWalk second year. I love watching movies, I love making art, and I love spending quality time with quality people. I was also that kid who was this close to doing engineering, but then I actually thought I'll do something I want to do. I've always loved the whole concept of filmmaking, how different groups of people with different sets of expertise come together to make something beautiful.
My name is Parinita Shinde and I'm a faculty member here at St. Joseph's College. I was once a student here not too long ago, and my experience as a postgraduate student of mass communication completely molded me as an individual. It was a very enriching experience. I was taught not to accept preconceived notions but rather to challenge them. When I came back a few years later to become a faculty member, it was surreal at first. It was an incredible opportunity, and I knew that it came with a lot of responsibility.
My name is Cynthia and I'm in my third and final year of visual communication. Art has always been a part of me, and the ability to create or reproduce something that could resonate with people is pretty cool.
As for this course, it tries to cover almost every aspect of filmmaking, from acting, editing, scriptwriting, etc. The college also conducts workshops for us where people working in the industry come and teach us a thing or two, and we can ask our queries, and it's all really quite fun. We also have really challenging final projects and assignments like shooting short films, writing scripts, and making music videos. It's all quite hectic, but it's all really fun at the same time. As for college life goes, I really didn't know what to expect, but I've really found some really good friends here, and they've given me some fond memories, and we're all really just helping each other out and hoping we reach somewhere big someday.
As a teacher of media studies, I try as much as possible to reconcile the curriculum with the real world scenarios. It's not about academic regurgitation, but rather about the holistic development of an individual. We try as much as possible to simulate newsrooms and the real world into the classroom and bridge the divide between media practitioners and media aspirants.
The thing with BBC is the exposure they give you kind of makes you want to do something about it, and the discussions you have in class make you think, and as a digital native that's very important. I mean, they teach you media law, but they also teach you the practical use and influence of the media. I still can't believe 3 years went by that quickly. I still remember my first memory over here was working for Allura, our department fest. We'd stay back every day working on props, and then that's how we got to know our classmates better, our teachers better. And I am so grateful for the friends I've made along the way. They are one of the best people I have met so far. And they're very supportive and talented, and BBC is all about that passion, and that includes the teachers. They are a talented bunch and they genuinely love what they teach, so that makes the learning experience so much better.
Research at St. Joseph's College is one of the prominent components, if not the most prominent component. We are basically a teaching institution, and the national average for teaching institutions in research is almost zero, and therefore whatever little you could do would actually make you into something important contributors to research. In fact, in some of our departments, our research is on par with the national average for research institutions. There has been research going on in departments of chemistry, physics, botany, other biological sciences. And in the social sciences, research has been happening in political science, English, and mass communication, and other departments, economics, and so on. The contributions from all these departments put together is very high compared to what one would expect from a teaching institution. And not only that, there is a lot of students participation in research. Most of the master's programs involve their students in research, and even some of the undergraduate students get into research through the term paper concept.
I really thank St. Joseph's College for the 3 years full of memories where I have met new people, gained so much of experience, gained so much of ground which will help me later in my future. So I just want to thank St. Joseph's College for all of these wonderful memories.
I would like to extend my gratitude to not just my friends, but also my professors and other non-teaching staff of our college who have helped me in this journey in St. Joseph's in these 3 years. Thank you.
On the whole, HTC has been a great part of this learning curve, and I'm thankful for it.
Because of the exposure I've gotten in college and the people I've met, it's made me grow as a person, and it made me who I am today, and I wouldn't have it any other way.
I thank the college for giving me a platform to showcase my talent in different ways. Thank you.
To top it all off, we have some really cool professors who make it worth coming to college every day.
and get access to both CuriosityStream and Nebula for a year. Sickle cell disease is a cruel genetic disorder that produces a defective form of hemoglobin, the protein needed by red blood cells to carry oxygen and deliver it to the body. The defective hemoglobin deforms red blood cells into irregular, sickle-shaped forms. These cells often block the bloodstream, causing organ damage and sometimes extreme bouts of pain. For one sickle cell patient, Victoria Gray, the disease has been crippling for her entire life. Much of her life has been punctuated by trips to the emergency room due to the pain, with life and career ambitions interrupted or put on hold. The sickle-shaped cells have damaged her heart, and many patients with sickle cell don't live beyond middle age. Strokes or heart attacks are a constant threat. Around 100,000 people in the US live with this disease. It is the most common inherited blood disorder and affects millions around the world, and it is notoriously hard to treat. Some patients can get help from drugs, and others sometimes undergo risky bone marrow transplants. But for many, these treatments are not enough to get rid of the constant burden of the disease. So when Victoria Gray was exploring the possibility of getting a bone marrow transplant, her doctors instead suggested something different. In fact, something profoundly different, to try to treat her disease. She jumped at the chance and would become the first patient in the US with a genetic disease to get treated with a revolutionary gene editing technique using CRISPR. And now, 1 year later, it seems to be working better than any doctor could have guessed. The billions of genetically modified cells doctors infused into her body appear to be alleviating virtually all the complications of her disorder. So what happened inside Victoria Gray's body that has left her almost completely free of the symptoms of her disease? Is the promise of CRISPR as a medical revolution starting to become realized? To understand how CRISPR is used today, let's go back to the beginning of its story. When CRISPR was first discovered in 1987, the researchers didn't really even understand what it is that they had found. While investigating a particular gene in E. coli, they noticed an interesting pattern in the DNA surrounding it. 5 identical sequences, each composed of 29 bases. These repeat sequences were separated from each other by 32 base blocks of DNA called spacers, which each had a unique sequence. The scientists wrote, "The biological significance of these sequences is not known." Over the next decade, these repeating patterns were found in many different microbes. Eventually, these patterns were given a name: clustered regularly interspaced short palindromic repeats, CRISPR for short. But scientists still didn't know what they were for, but certain observations about them started emerging. They were always next to specific enzyme-producing genes, labeled as CRISPR-associated genes or Cas genes. Cas genes encode enzymes that can cut DNA, but at the time, no one knew why they did so or why they were always next to the CRISPR sequence. Soon, scientists noticed something else about these DNA sequences: that the CRISPR spacers, the variable sequences in between the repeating sequences, looked a lot like viral DNA. And with this revelation, the purpose of the CRISPR sequences started to become clear: that these repeating patterns are a weapon that the bacteria were using against viruses. When a virus infects a bacteria, it injects its genome into the cell. If it is a previously unseen virus, a new spacer is derived from the virus's genome and is incorporated into the CRISPR sequence. The spacers are essentially a history of old infections, so the bacteria won't be infected again. The CRISPR sequence is then transcribed, creating short CRISPR RNA molecules. And those repeating palindromic sequences? Their palindromic nature means that these sequences in the CRISPR RNA can fold in on themselves, creating a hairpin structure. The CRISPR guide RNA then binds with the matching viral DNA. The Cas enzyme then cuts and destroys the invading viral genome, with the hairpin structure helping the Cas enzyme to cut exactly where it's supposed to. And with a broken genome, the virus can no longer replicate itself, and the infection comes to a halt. When scientists realized that these microbes are effectively programming their enzymes to seek and destroy specific sequences of DNA, the significance of the discovery started to sink in. This could be used as a tool. In the past, researchers had been able to use restriction enzymes to cut up DNA, but this did so in an indiscriminate way. The CRISPR-Cas system instead could make precise cuts, giving rise to a whole new area of science, what we now know as gene editing. CRISPR technology allows genetic material to be added, removed, or altered at particular locations in the genome, much like hitting Ctrl+F on your keyboard, finding a word in your document, and deleting, changing, or replacing it. In order to harness the power of CRISPR in the lab, scientists first design and synthesize short guide RNA molecules that match the sequence of a gene they want to edit, usually about 20 base pairs long. Then, like in the targeting step of the bacterial system, this guide RNA shuttles the Cas enzyme, usually the Cas9 enzyme, to the intended DNA target. The Cas9 enzyme then makes a cut across both strands of the DNA. At this stage, the cell recognizes that the DNA is damaged and tries to repair it. Scientists can use the cell's own DNA repair machinery to add or delete pieces of genetic material, or to make changes to the DNA by replacing an existing segment with a customized DNA sequence. And this brings us to Victoria Gray and her sickle cell disease treatment. While sickle cell is indeed a genetic disorder, her treatment did not involve going in and deleting or changing the genes that lead to the disease. Instead, scientists found a way to almost completely alleviate the symptoms. The treatment, called CTX001, tackles the disease by boosting the production of fetal hemoglobin, HbF, a type of hemoglobin that is present at birth but then stops being produced. The idea is that restoring the production of fetal hemoglobin can compensate for the defective hemoglobin produced by sickle cell patients. To do this, doctors first harvest stem cells from the patient's bone marrow. Then, the CRISPR-Cas9 components are delivered to the cells, where they then create a deletion in the gene BCL11A, which encodes a transcription factor that normally represses fetal hemoglobin synthesis. This breaks the gene and allows the cells to resume making the protein. Billions of these modified stem cells are then reinfused into the body. They won't replace all of the existing stem cells, but if enough of them successfully implant and start producing the needed protein, then the treatment will be effective. Doctors hoped after the treatment that 20% of the hemoglobin in Victoria Gray's body would be fetal hemoglobin, but the results have far exceeded expectations. 1 year after the treatment, about 46% of her hemoglobin is now fetal hemoglobin. Additionally, 81% of her bone marrow cells now contain the genetic modification needed to produce the fetal hemoglobin protein, indicating the edited cells have continued to survive in her body for an extended period. Gray's life before the procedure was a constant cycle of dozens of blood transfusions and hospitalizations every year. And now, after the experimental procedure, those numbers have been brought to zero. She hasn't had any pain attacks, emergency room visits, or needed any blood transfusions since the procedure. And while Gray was the first patient to receive this experimental treatment, she was not the only one. Patients with beta thalassemia have also received CTX001 to restore fetal hemoglobin production. Their blood disorder causes them to not produce enough normal hemoglobin. But gene therapy in several of these patients have left them no longer needing blood transfusions for months now. So is this a cure for these blood disorders? Not exactly, but gene therapy like this can potentially prevent many, if not all, of these diseases' complications. And the change to these particular patients' lives can't be overstated. However, the treatment is not without its downsides. Just like for a typical bone marrow transplant, recipients of the CTX001 treatment have to undergo chemotherapy to eliminate their own bone marrow to create space for the injection of modified stem cells. And just like the chemo for cancer, this comes with grueling side effects. Fatigue, nausea, mouth sores, loss of appetite, hair loss. It is not trivial. Gene therapy like this is not the same as taking a pill or a drug. It's more like getting an organ transplant. And much like cancer treatment, it will not come cheap. And even though the results from these studies have been many questions that are still to be answered. Will the treatment keep working for months or years to come? Will it help these patients live longer? Is it safe in the long term? And will there be any unintended side effects? While these questions do remain, It is impossible not to feel optimistic when hearing about these extremely positive results. And these blood disorders are just one of many things that CRISPR has begun to tackle. Scientists have started researching CRISPR to reverse genetic blindness, muscular dystrophy, cystic fibrosis, and even cancer. And even though gene therapy treatment is expensive, CRISPR technology is in general cheap to test. In the past, it might have cost thousands of dollars and weeks or months of fiddling to alter a gene using old-school knockout techniques. Now it costs in the hundreds of dollars and takes just a few hours. There is still much research to be done, and scientists are just scratching the surface of what is possible with this technology. We can't yet know the exact effect that CRISPR will have in our futures, but it is going to be huge. Science has progressed towards a much better understanding of genetics, but there is still so much we don't know. In many ways, our genes are a book that can be read to determine our destinies, leading to our good health or sometimes our unfortunate illnesses. But scientists are becoming more aware that DNA doesn't explain everything, and that our environments and our experiences play a greater role in how our genes are expressed than previously understood. If you want to learn more about how environmental factors can determine which genes are turned on and off, then you should watch Our Genes Under Influence on CuriosityStream. It's a 50-minute in-depth film that explores how identical twins with the same DNA can be physically different, how generations of plants can be physically modified without changing the DNA sequence at all, and how epigenetics shapes our biology more than you might realize. CuriosityStream has thousands of high-quality documentaries like this one, about everything from genetics, technology, space, or nature. There are even a handful of David Attenborough documentaries, which, if you're like me, you know are obviously the best ones. And to make it even better, CuriosityStream has partnered with Nebula, which is the streaming platform created by me and over 100 fellow educational YouTube creators. It's a place where we can express ourselves completely
Yeah, Samson.
Beatrice ma'am, Dr. Ghosh has come. He's in the
Yes.
meeting. Yes,
So
ma'am.
I'm just connecting my earphones. 1 second. Uh, Hello.
Hello.
Yeah. Good afternoon, Dr. Ghosh.
Good afternoon.
This is Beatrice here.
Hello, Beatrice.
Yeah. Welcome, sir, for the.
Thank you. So,
I think they're starting at 1:15, right?
1:15, yes.
I hope you had your lunch, sir.
Yes. So, how do I share my screen? Oh, you will have
Samson?
to share it.
Can you
Yes. No,
help,
sir.
sir?
Yes, ma'am. So, you will, a student moderator will just give a brief introduction about you. After that, I will give you presentation rights and you can share your screen.
Okay, all right.
Thank you, sir.
Sure.
Is Samson, is Sumeru here?
Yes, ma'am. He's in here.
Okay. And Calrida?
Calvert as well.
Okay, have I pronounced your name correctly now, Calrida?
Yes, ma'am. Thank you.
Okay.